Hello and welcome to MOOC on Applied Electromagnetics for Engineers. In this module we will continue the discussion of transient propagation, that is propagation of transient voltages in the time domain on a transmission line circuit. So consider the example that is given here. Of course we will be using the lattice diagram that we developed in the last module in order to solve the following problem. So we have a battery which is producing a 4 volt DC voltage. Okay, it has an internal resistance of 150 ohms. It is connected to a transmission line circuit which is 900 meter long and terminated in an open circuit. Okay, the characteristic impedance of the transmission line is 50 ohms and the velocity over which the waves would propagate, the voltage would propagate on this transmission line is 3 into 10 to the power 8 meter per second. So what we want to know is to find out what is the voltage at Z equal to 600 meter. That is, we will imagine that we are keeping a oscilloscope here. Okay, this oscilloscope will be kept at 600 meters, which is about 2/3 from the source side. Okay, and we want to find out what is the voltage that we would observe on the on the scope for, let's say, up to 12 microseconds. So up to 12 microseconds we want to know what is the voltage measured at this point on the transmission line, which is about 600 meters. It may not be nicely written here, but this is 600 meter from the source. So our coordinate system is Z equal to 0 at the source or the generator side and Z equal to 900 meter in this case, because the length of the transmission line is 900 meter on the load side. Okay, we not only want this, we also want to find out what is the distribution of the voltage across the length of the transmission line at t equal to 10 microseconds. So imagine that you actually are able to take a snapshot of the voltage on the transmission line at a time of 10 microsecond, and we would like to know what is the voltage at different points in the transmission line, the voltage distribution on the transmission line at t equal to 10 microsecond. Now we will be using the lattice diagram that we discussed in the last module. Remember what a lattice diagram is. On the one axis you had the length of the transmission line, that was the coordinate or the ordinate there, which was z axis, and on the other axis you had the time axis. So this was also called as a space time diagram or also called as a bounce diagram, because voltages would be bouncing back and forth. And I told you that there are two initial steps to begin drawing the lattice diagram. The first step is to calculate what is the reflection coefficient at the load side, as well as, because there will be reflections from the generator side, so calculate what is the reflection coefficient at the generator side. So calculate both gamma g and gamma L, okay, and put that one down on the lattice diagram. Then you need to calculate what is the first amplitude of the first forward voltage, and that will be obtained by the voltage divider that is formed by Rg, the generator impedance or the generator resistance, and the transmission line characteristic impedance and whatever the voltage that you have connected. So let us first calculate, as part of that strategy, let us first calculate what is gamma g. Gamma g clearly is given by 150 minus 50, 150 being the generator impedance, divided by 150 plus 50. So this is 100 by 200 or equal to half. Similarly, what is the load reflection coefficient? By now you know that the open circuited load will have gamma L equal to plus 1. Just for our reference, we will also note that gamma g is positive and gamma L both are positive numbers. That is, the sign of these two are positive numbers, indicating that Rg is greater than R0, RL is also greater than R0. So this is the first step of calculating the reflection coefficient. The second step would be to calculate what is the initial amplitude or the amplitude of the first forward voltage, which we denoted as V1 plus. V1 plus in this case is the voltage divider that would exist between the generator impedance of 150 ohm and the characteristic impedance of 50 ohm. So V1 plus is given by 4 into 50 divided by 150 plus 50. So this 4 into 50 is 200 divided by 150 plus 50 is 200. So this is equal to 1 volt. So you have a 1 volt initial forward propagating voltage launched on the transmission line at the time t equal to 0. Okay. So now what will happen? How do we write the lattice diagram? So we go to the lattice diagram here. On one axis we draw the z axis, and down here I will draw the time axis. Okay. So I know what is the length of or the time delay of the propagation. In order to find the time delay, I go back to this circuit. I know that the length of the transmission line is 900 meter. Okay. So time delay will be given by 900 meter, and we know that the velocity is 3 into 10 to the power 8 meter per second. So this is about 3 microseconds. Okay. So what we have is 3 microsecond. So let us now build the lattice diagram. So first you would have a V1 plus launched. Okay. V1 plus we calculated was 1 volt. So 1 volt is launched at t equal to 0, and it reaches z equal to 900 meter, that is the load side, at 3 microsecond, at which point it gets reflected back because there is an open circuit with a reflection coefficient of 1. So please note that I am actually writing both the reflection coefficient as well as the amplitude of the voltage that we have received. Okay. So this is a good practice to remind ourselves that what is happening to the voltage as well as the reflection coefficient. So we won't make any mistake. So let me rewrite gamma L equal to +1 here and gamma G equal to +half on this side. So 1 into 1 volt begins to propagate back. This is true because an open circuit simply reflects the voltage back. So once it reaches the generator side at 6 microsecond, there will be further reflection. So this was V1 plus, the next one was V1 minus. Now you have V2 plus with an amplitude of half into 1, which is equal to half voltage, right. So half voltage would begin to propagate at t equal to 6 microsecond and reaches the load at 9 microsecond. There will be one more reflection of half voltage because the reflection coefficient here is equal to +1. Then there will be further reflection. The reflected half voltage will reach at 12 microsecond, whereas the further reflection of 1/4 voltage will begin to propagate from 12 and will reach at 15 microseconds. So let us stop here, not because I just ran out of the space here, but also because the voltages keep on reducing, and we also have enough information to solve the two questions that were posed to us. The first question was, what is the voltage distribution along the entire length of the transmission line at a fixed time of t equal to 10 microsecond? In order to answer that, we need to look at our lattice diagram and first locate where 10 equal to microsecond occurs. So let me locate 10 equal to microsecond. So this is about 10 microsecond. Now if you look at the transmission line, on the transmission line, if you want to find out the entire distribution, right. So this at 9 microsecond, the voltage would be reflected, the reflected voltage of half volt has begun to propagate, right. It has begun to propagate and it has reached this particular point. So the total time elapsed here is 1 microsecond after 9 microseconds. So the total time is about 1 microsecond, and in 1 microsecond what would be the length of the transmission line that the voltage waveform would cover? We know that the entire length of the transmission line is 900 meters and it requires 3 microseconds for the voltage wave to go from one end to the other end. Therefore in 1 microsecond you are able to go 300 meters. So in this case, since it is 10 microsecond, the point where this, the blue line, which is how the voltages are propagating, is meeting the time axis which I have drawn, a slice of time, as I can call the slice of time which I have drawn is at 10 microsecond. So this point would be 300 meter away from the load, but 300 meter away from the load is nothing but 600 meters. Okay. So we would have actually reached at the 600 meter. Please note that the voltage half has not propagated here. So the voltage has actually not propagated to this side. So this side voltage would still be seeing whatever the voltage that was there earlier. And what is the earlier voltage to this? That would be half volt, and this would again be half volt, and so on and so on. Okay. So let us now plot what would be the voltage distribution that would be present throughout the section of the transmission line at a time of 10 microsecond. So let us see how this would be. So I need to plot the voltage as a function of Z here because I am taking the snapshot in time. Let me mark 3 points corresponding to 300 meters, 600 meters and 900 meters. So obviously I am measuring Z in terms of meters. So this is the origin, which is 0 meter. This corresponds to the sending end, okay, and this corresponds to the load or the receiving end, or the load side, or the load at the end that we have connected. So if I am, for example, let's build up it in this way. Suppose I am there at 300 meter, okay, so 300 meter would correspond to some point over here, and I keep moving forward in time. So at some particular time I have a voltage, incoming voltage of 1 volt, then after a certain time there was one more volt that was coming in. So therefore the voltage at this point of time on the 300 meter distance from the transmission line would be 1 plus 1, that would be 2 volts. So initially it was 1 volt, that jumps by a 1 volt when this reflected voltage 1 volt reaches from this side, V2 minus reaches, V1 minus reaches here. Continue along, there would be one more jump of half a voltage. So now the total voltage is 1 plus 1 2, 2 plus half, which is 2.5, and then we keep coming in over here, and we need to stop at this point. This is very important. I need to stop here because this is the time slice I have taken. So up to 10 microsecond, this is what the 3 voltages that I have received, and you can clearly see that I can take slices along Z at any point, and clearly the voltage that I would be obtaining would all be constant, and all will have an amplitude of 1 plus half, which is 2.5 volt. Only in this region, beyond the red line region, the total voltage will be 1 plus 1 2, 2 plus half plus another half because of the reflection. So that would be 3 volts. So you will have 1 plus half plus the half voltage that would have propagated, the half wave would have propagated from the load side until about 600 meter. So the voltage distribution, if I plot the voltage distribution up to 600 meters, it would be 2.5 volt. However, from 600 to 900 would be a voltage of 3 volt, and a 0.5 volt step is actually propagating from the load side towards the generator. So this is the answer to the previous, one of the questions that we asked. What is the voltage along the entire transmission line? What is the voltage along the entire transmission line at a snapshot time of 10 microseconds? So this is the answer. We also have asked another question. So we asked another question which said that what would be the voltage distribution at some at Z equal to 600 meter. So imagine that we have kept an oscilloscope there, right? So we kept an oscilloscope and we want to find out what is the voltage, and we want voltage up to say 12 microsecond. So let us begin to first write down the voltage axis. So I have T measured in microsecond. This is 3, this is 6, this is 9, this is 12. So we need to come up to 12 microsecond. How do we do that? Again, look at the red line. At 600 meter, I have actually dropped this particular line, right? So you follow this through. How much time would be required for the voltage that is launched at the source side, that is at Z equal to 0, to reach Z equal to 600 meters? Well, this has about 1 microsecond per 300 meters. So there are distance that you need to calculate is 600 meter. So from the source it will take 2 microseconds to reach 600 meter, but from the load you will only take 1 microsecond. Therefore, the cut or the meeting point or the intersection point between the blue line and the red line is happening at 2 microsecond, indicating the voltage propagation from the generating end to this 600 meter section, and then at 4 microsecond, because remember there is only 1 microsecond delay from the load side for the voltage to reach 600 meters, it is pretty close to the voltage. And then next will be 6 plus 2, that would be 8 microsecond, and the next slice that we have will be at 10 microsecond. Anyway, nothing would happen at 12 microsecond, therefore we can even stop this one at 10 microsecond. So at 2 microsecond we see a jump of 2 volt, okay, so this is the 2 volt, and at 4 you would see a jump of another plus 1 volt. So, there will be a further jump of 1 volt. So, this is 1 volt plus a jump of 1 volt makes it 2 volts. So, this is the jump 1 volt that we have, and this would happen at 4. Sorry, let me redraw this one in a slightly bigger scale. Okay. So, let us draw here. So, what I am looking at is the voltage as a function. So, T is in microsecond, the voltage at Z equal to 600 meter as a function of time up to 12 microsecond, but we anyway have seen that whatever we need to find, that information that up to 10 microsecond is sufficient. So, 3, 6, 9 and 12, because no change happens at 12. So, what is the voltage? So, initially you have a voltage jump of 1 volt at 2 microseconds. So, this is the 1 volt pulse, and at 4 microsecond there will be a further jump. Okay. And this further jump is also of the same magnitude 1 volt, therefore, you go to 2 volts. So, the jump here itself is 1 volt, and this continues to be the case until you reach 8 microseconds. Okay. So, this was at 8 microsecond where you would reach one more jump, and this time the jump is about half volt. So, you will go to 2.5, and after that at 10 you will again reach a jump of another 2.5. So, it becomes 3 volts. So, here there was a jump of 0.5. So, this is 2.5 volt. So, I would suggest that you actually look at this diagram carefully and then convince yourself that the values that we have written is correct. If there is any mistake in the calculation, please make corrections accordingly. So, you can see that the voltage is steadily increasing, and eventually what would be the voltage that you should see on the transmission line? Well, remember, this is an open circuit, right, and an open circuit would have a full voltage across it, and the line is lossless. So, no matter what line that we have connected, as long as it is lossless, the voltage that you would see on an open circuited end of the transmission line will be the full value of Vg. So, here you had some Rg, and after time where the transients have settled down and you have reached the steady state, you should see a full voltage of Vg, and that would be the voltage distribution along the entire length. What would be the current distribution? Well, current would be equal to 0 in the case that you are taken an open circuit. Eventually you will see that the current is 0, but mathematically these values are reached at asymptotically in time, that is, they will be reached eventually, but if you wait for sufficient microseconds long, then the voltage would have reached almost the open circuit voltage, and therefore these values are all right. Okay. So, you see a steady climb or an overdamped climb towards 4 volt. Okay. So, this is what is a solution for this problem. Before dropping this transient propagation, let us consider one more case. Okay. In this case, we will consider a Rg of 150 ohms as we considered in the previous case. So, this is the other example that I would like to consider. So, we consider Rg of 150 ohms, RL of 25 ohms. So, you can now see that gamma L will be negative and gamma L will be equal to minus 1 by 3, where I am assuming R0 is still equal to 50 ohm. The length and other values are all the same, and what I want is again to see what is the voltage at 600 meter as a function of time up to say 10 microseconds, okay, 10 or 12 microseconds. I will construct the lattice diagram over here first. All the values that we require are already here. Gamma G is equal to half gamma L is equal to minus 1 by 3. This is at 900 meter, this is at Z equal to 0 meters, okay. So, we begin with a V1 plus, which is the same as the previous case, which is 1 volt. So, the 1 volt wave propagates from the receiving side and reaches the load side, at which point it gets reflected. What is the reflected voltage amplitude? Minus 1 by 3. Again there will be one more reflection of minus 1 by 6 volt, because minus 1 by 3 gets multiplied by half, therefore this becomes minus 1 by 6. A further reflection will be at plus 1 by 18 volt. So, you can see 1 by 18 is almost very small, and it just keeps on reducing. And what are the different time slices that these voltage changes are happening at the load side? This would be at 3 microsecond, and then at the source would be changing at 6 microsecond. Further change in the load voltage happens at 9 microsecond and at 12 microsecond. So we want to find out what is the voltage as a function of time at a fixed distance along the transmission line, which is at z equal to 600 meter. Okay. In order to do that, we go back to the same condition. We drop a line, okay, or a slice at z equal to 600 meter, and we need to drop this line until 10 microseconds. So 10 microsecond happens to be here somewhere, so we can drop a line at 10 microseconds. So this is 10 microsecond and we have dropped it. Now it is easy for us to see what is happening. At 2 microsecond you will see a voltage jump of 1 volt, okay, and at 4 microsecond, remember, because this is, so where are the slices located? This is at 2, this is 4, this is 8, so this is at 10. I made a small mistake here. So wherever we drop, that would be the line which corresponds to the intersection point, right? So we have this line, and you have a voltage going back which was 1 by 18 volt, okay. So we have changes happening at 2, 4, 8 and 10. At 2 you will see a jump of 1 volt, okay, and at 4 you will see one more jump, but this time the jump is in the negative direction because the value of the reflected voltage is minus 1 by 3. So you will see 1 minus 1 by 3 volt propagating. So what is 1 minus 1 by 3? This is 2 by 3 volt, okay. So you will actually see that the voltage has dropped from 1 volt to 2 by 3 volt. The change is happening at 2 and a jump happening at 4. This continues until you go to 8 microsecond. So this time is measured in microsecond, of course. So at 8 microsecond you will see further jump of minus 1 by 6. So the voltage would drop to 2 by 3 minus 1 by 6. So I can multiply both sides here by 2. This becomes 3 by 6. 3 minus 1 by 6 is 1/3. So it is still positive, but it would be 1/3 voltage at 8, and at 10 microsecond you would see a jump, and this time the jump is slightly positive because 1 by 18 volt, and this is how you actually start seeing. So if I have got the numbers wrong, please sorry, this number is actually 4 minus 1 3, right. So this is not 1 by 3, but this would be 4 minus 1 by 6, which is 3 by 6, which is equal to half voltage. So this voltage value here, let me draw it here, is actually half voltage, and the voltage at this point is half plus 1 by 18 volts. So this is the voltage as you would see at 600 meter, and you can clearly see that this is of the form which is oscillating, okay. So this is an example of a under-damped system. So why is this an under-damped system? Because at least one of the gammas has become less than 0. So sign of gamma is less than 0 indicates that one of the resistances, it could be either Rg or RL, has become less than R0, and this is the only condition that you should have. You should not have both having less than 0, okay. As a final example, let us consider the propagation in the same situation of a transient, but this time we short circuit the load, okay. So let us short circuit the load. So clearly short circuiting the load will give me gamma L of minus 1. I keep all the other parameters to be the same. So I still have a 900 meter 50 ohm characteristic impedance transmission line connected, okay, to a load of, so connected to a generator of 150 ohm impedance and a step voltage of, or a battery voltage of 4 volt, okay. So I will not completely solve this one, I will just write down the lattice diagram. I hope you will be able to follow this. Because gamma L is minus 1, whatever the voltage that we receive, so initial voltage that would be launched will be 1 volt as in the previous case, but this time there will be a reflection of minus 1 volt, because the 1 volt that we receive at the load side will be multiplied by gamma L equal to minus 1, and therefore the reflected voltage will be minus 1 volt. There will be one more reflection from the generator side, because the generator is about half, the gamma G is half, so the reflected voltage is minus half volt, and there will be a further reflection from the load side which would be half volt, okay. The sign here has become negative because gamma L is negative. Okay. So let us now plot and see what kind of a voltage we would see, but this time I want to plot the voltage at z equal to 0, that is I want to plot the voltage at the source or the generator side. So where are the changes happening? The propagation delay is 3 microseconds. So changes at the source happens at 0, 6 microsecond and 12 microseconds. So this is 6, 12, and at this point there would be another 1 by 4 voltage going backward. So that I would need it, right. So 9 microsecond. So let us put down the numbers of 3, 6, 9 and 12 and see what kind of voltage changes will happen. So at 0 you have launched a 1 volt which changes to 0 volt at 6, right. See, you have launched a 1 volt which begins to propagate, okay. At 6 microsecond you have received a minus 1. So 1 minus 1 will make it 0. So that is what you would initially think. However, there is also a minus half volt generated from the generator end and that begins to propagate. Therefore, the voltage at this point is minus 1 minus half plus the previous 1 volt. 1 and minus 1 will cancel, a minus half would still be there. So the voltage here would be minus half, and this would be present until you get to 12 volt, at which point a plus half volt coming in from the load side would make this voltage go to 0. However, there is a 1 by 4 volt reflected signal from the generator end which is beginning to propagate, and therefore the voltage here is about 1 by 4 volt. You can clearly see where this is going, because after at 12 you will get the 15 microsecond point at which there will be a minus 1 by 4 reflected off the load side, okay, and then there will be one more reflection from the generator side. It won't be at 15, sorry, this would be at 12 plus 6, that would be at 18 microsecond. Okay, so let me redraw this one. So at 18 microsecond, so this is 12, so let us say this is 15, so this is 18, and there was a plus 1 by 4 voltage generated and propagated at 18. Because of the reflection at this point of minus 1 by 4, this would initially go to 0, but then minus 1 by 4 would be reflected further with a half, or with a value of half multiplied by minus 1 by 4, which is equal to minus 1 by 8 volt. So it would just go slightly below, become minus 1 by 8 and eventually go up, and then keep doing this, reaching a steady state voltage of 0 volt. Does this make sense, this steady state voltage of 0 volt? Yes, of course it makes sense, because you have a short circuit at the load side and the voltage at the short circuit will be equal to 0. Again you will see that because one of gamma L has become negative, there is an underdamped or an oscillatory kind of a behavior. So you would see that there is an oscillatory kind of a behavior. Okay. So in order to obtain underdamping situation, you need to have one of the gamma go to 0. If both gamma are less than 0 or greater than 0, then you go to what is called as the overdamped case, in which there would be a staircase kind of a thing. So it would actually keep increasing and eventually reaches the steady state value. So this completes our discussion of transient voltages on the transmission line. We have looked at important cases, if you are considering a power transmission cable, if a lightning hits, then we know how this lightning would propagate. That depends of course on what is the transmission line to which it is connecting. So thank you very much.